This course provides an introduction to ARM-based system-on-chip design. Let's break that down to understand our journey. First, system-on-chip, which you'll often see abbreviated as SoC. What does that mean? Well, think about a traditional computer. It has a motherboard with many separate components, a processor, memory chips, graphics cards, and so on. An SoC takes all of those essential functions and integrates them onto a single, tiny piece of silicon. It's literally a whole system on one chip. This is the technology that makes our smartphones, tablets, and smartwatches so powerful, yet so small and power efficient. Next, we have ARM-based. ARM is a type of processor architecture. It's incredibly popular, especially in the world of mobile and embedded devices.
Why?
Because ARM processors are designed to be extremely power efficient. They deliver great performance without draining your battery quickly. So when we say ARM-based, we mean we're focusing on designing SoCs that have an ARM processor at their core. Finally, the word design. This tells us that we're not just going to learn about SoCs. We're going to dive into the process of how they are actually created. We'll be looking at the methodologies, the challenges, and the steps involved in building these complex integrated circuits. So, altogether, this course will guide you through the fundamental principles of designing complete computer systems on a single chip, with a focus on the ARM architecture that powers so much of our modern technology. This slide gives us a clear roadmap of what we'll be covering in this module. Think of it as our journey plan for understanding ARM-based system-on-chip design. First, we'll start with the why. We'll explore the motivation behind the whole idea of a system-on-chip, or SoC, design framework. Why has this become such a dominant approach in modern electronics? What problems does it solve? Next, we'll move on to a balanced view of the technology. We'll weigh the pros and cons by looking at the advantages and limitations of SoCs. This will help you understand when an SoC is the right choice for a project and what trade-offs might be involved. After understanding the what and why, we'll dive into the how. We'll walk through the typical SoC design flow. This is the step-by-step process engineers follow to take an idea and turn it into a physical chip. Then, we'll look at a particularly interesting and flexible variant called the programmable SoC, or PSoC for short. We'll discuss what makes them programmable and why they are so useful. To bring all these concepts together, we'll tackle a practical exercise, designing a simple ARM-based SoC. This will give you a concrete feel for how these different components and ideas we've discussed actually come together in a real-world example. Finally, for those of you who want to dig even deeper, we'll end with a bibliography. This will point you to some excellent books and resources for further study. So, it's a comprehensive journey from the fundamental motivation right through to a practical design example. This slide gives us a roadmap of what we'll be covering in this section. Think of it as our journey's itinerary. First up, and it's highlighted because this is where we're about to start, is the motivation of SoC design framework. We'll explore the fundamental reasons why we design systems this way. Why is system-on-chip, or SoC, such a big deal in modern electronics? What trends are driving this approach? After we understand the why, we'll move on to the what. We'll examine the advantages and limitations of SoCs. Every technology has its trade-offs, so we'll look at the good parts, like performance and power efficiency, and also the challenges, such as a lack of flexibility. Next, we'll get into the how by looking at the SoC design flow. This is the step-by-step process, the blueprint that engineers follow to take a concept and turn it into a physical chip. Then, we'll discuss a really interesting variation called programmable SoC, or PSoC for short. We'll see how these devices combine the power of a standard SoC with the flexibility of programmable logic, which opens up some amazing possibilities. Following that, we'll get our hands dirty, conceptually at least, by looking at the process to design a simple ARM-based SoC. This will help tie all the theory together with a practical example. Finally, we'll wrap up with a bibliography, pointing you to some excellent books and resources if you want to dive even deeper into this topic. So, let's begin with our first topic, the motivation for the SoC design framework. This page really sets the stage for our entire discussion by asking a fundamental question. Why do we need to think about designing a system on chip, or SoC? What's the motivation? The first point tells us we are living in a post-PC era. This doesn't mean personal computers have disappeared, of course, but they're no longer the only, or even the main, way we interact with technology. Think about the devices you use every day. We have smartphones and tablets, which are incredibly powerful computers in their own right. Beyond that, we have the Internet of Things, or IoT, smartwatches, fitness trackers, smart home devices. All these connected gadgets are part of this new era. This also extends to larger concepts like cyber-physical systems, where computing is deeply embedded into physical processes, and Industry 4.0, which refers to the new wave of smart, automated manufacturing. Now, what powers this entire revolution? At its heart, it's the same fundamental component, the silicon transistor. This tiny electronic switch is still the engine driving all of modern electronics. However, and this is the crucial point, our priorities for designing silicon chips have changed dramatically. In the past, especially during the desktop PC boom, the primary goal was raw speed, measured in clock frequency, the gigahertz race, as it was called. But for a device you carry in your pocket, pure speed isn't the only thing that matters. The key metrics have shifted. Today, designers are focused on three things: cost, form factor, and power. Form factor simply refers to the physical size and shape of a device. A smartphone needs to be thin and light. A wearable needs to be even smaller. So, the chips inside must be tiny. Power is all about energy efficiency. We need our devices to have a long battery life, so the chips must perform their tasks while consuming as little energy as possible. And cost is always a factor. To make these devices accessible to everyone, the components must be affordable to produce in massive quantities. So, how do engineers meet these new demands for small, low-power, and low-cost computing? The answer lies in the next point. On-chip integration of functional hardware is now more important than ever. This is the very definition of a system on chip. Instead of using a large circuit board with separate chips for the processor, graphics, memory, and communications, we integrate all of those functions onto a single piece of silicon. This integration is what allows us to build the powerful, portable devices that define the post-PC era. The final question on the slide, how and why have we reached this point, serves as a perfect transition. It prompts us to look at the historical and technological trends that have made this massive integration both possible and necessary. We'll start exploring that with the very famous principle known as Moore's Law on the next slide. This brings us to one of the most fundamental concepts in the history of modern electronics, Moore's Law. The man in the picture on the right is Gordon Moore, a co-founder of Intel. Back in 1965, he made a very insightful observation that became a self-fulfilling prophecy for the entire semiconductor industry. Let's break down the graph to see what he observed. The horizontal axis represents time, moving from 1970 towards the present day. The vertical axis shows the number of transistors on a single integrated circuit or chip. Now, pay close attention to the scale on this vertical axis. It doesn't go up evenly like 1, 2, 3. Instead, it jumps by a factor of 10 each time, from 10 to the power of 3, which is 1,000, to 10 to the power of 4, 10,000, and so on, all the way up to 1,000,000,000. This is called a logarithmic scale. On a graph like this, a straight line doesn't mean steady. linear growth. It means explosive, exponential growth. Each data point on this line represents a famous processor from its time. Down at the bottom left, you see chips from the 1970s like the Intel 4004, which had just over 2,000 transistors. As we move across the years, you see the numbers skyrocket. We passed the Pentium processors in the late 90s with millions of transistors, and then the AMD and Intel Core series in the 2000s, pushing into the hundreds of millions and even billions of transistors. So, what is Moore's law? It's the observation that the number of transistors on a chip doubles approximately every 2 years. This isn't a law of physics, but rather a projection of a trend. However, it became a goal for the industry. Companies plan their research and development around this expectation, pushing innovation to keep the trend going. This law is the direct answer to the question from the previous page. How and why have we reached this point? The ability to pack more and more functional components into a smaller and smaller space is what has fueled the entire digital revolution. It's why a smartphone in your pocket today is vastly more powerful than a room-sized computer from decades ago. This incredible density is what makes System-on-Chip, or SoC, design possible in the first place. You need to be able to fit billions of transistors on a chip to integrate a processor, memory, graphics, and other peripherals all together. So, Moore's law describes what has been happening, this doubling of transistor density. But it naturally leads to another question. Why did this happen? What is the benefit of this constant scaling? We'll look at the powerful cycle that this scaling creates on the next page. This page answers the fundamental question. Why do we keep scaling? We just saw Moore's law on the previous page, which describes how transistors get smaller and more numerous over time. This diagram explains the powerful engine that drives that trend. It's called the virtuous circle of the semiconductor industry. A virtuous circle is a cycle where each step positively reinforces the next, leading to continuous improvement. Let's walk through it. We can start anywhere, but let's begin with investment. To make computer chips, you need incredibly complex and expensive factories called semiconductor foundries or fabs. Building and equipping these requires massive financial investment, often billions of dollars. This investment enables the next step, transistor scaling. This is the practical application of Moore's law. The money is used to develop new technologies and manufacturing processes to shrink the size of transistors. When we scale transistors down, we can fit more of them onto a single piece of silicon. So, why is that good? This leads us to the next point in the circle, better performance/cost. Smaller transistors bring huge benefits. First, they're faster because the electrical signals have less distance to travel. Second, they consume less power. And most importantly, from a business perspective, the cost per transistor drops dramatically. This means we can either make much more powerful chips for the same price or make chips with the same capability for a much lower price. This improvement in performance and cost is what makes the magic happen. It enables the creation of novel applications. The powerful, low-cost chips that result from scaling allow engineers to design products that were previously science fiction. Think about the smartphone in your pocket. It's a powerful computer that wouldn't be possible without cheap, high-performance, low-power processors. The diagram shows a central chip enabling all sorts of devices, cars, cameras, gaming systems, and more. These new, exciting products create market growth. As you can see from the images of laptops, cameras, and music players, people want to buy these new gadgets. This creates enormous new markets and drives huge revenue for the companies that make them. And that brings us right back to the beginning of the circle. The profits generated from this market growth are then reinvested into building the next generation of even more advanced factories, which allows for even more aggressive transistor scaling. And the cycle repeats, spinning faster and faster. This virtuous circle is the core reason for the rapid technological advancement we've seen in the last 50 years. However, as we'll see on the next page, this incredible pace of increasing complexity also creates a major challenge for the people who have to design these chips.